This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
I want you to close your eyes for a second, assuming you're not driving, of course, and just think back to the hottest, most intensely oppressive summer day you have ever personally experienced.
Oh, yeah. We all have that one day seared into our memory.
Exactly. You know the exact kind of heat I'm talking about. It's that day where the heat doesn't just feel like a number on your weather app. It actually feels like a physical weight. It's totally inescapable.
No, right. You step outside.
You step out your front door, and it almost feels alive, like it's actively pressing down on your chest, radiating right up through the rubber soles of your shoes from the asphalt.
It's the kind of day where even the shadows offer zero relief. You take a breath, and the air itself feels exhausted, like it's been baked in a kiln.
Yes. And your instinct on a day like that is entirely defensive, right? You retreat. You find shade. You find a fan. You crank up the air conditioning if you're lucky enough to have it, and you just hunker down and wait for it to pass.
Because we're conditioned to think of heat waves as just, weather.
Right, a temporary spike. Just an uncomfortable afternoon that the evening breeze will eventually sweep away. But what if that instinct is completely wrong?
It is wrong. That's the terrifying part.
What if, while you and I are hiding indoors waiting for the thermometer to drop, that heat wave is actually outside operating as a massive, invisible engine? An engine that is actively, fundamentally restructuring our global climate and acting as a catalyst for just large-scale environmental destruction.
And that is exactly the paradigm shift we're looking at today. We are tracking the unprecedented evolution of the modern heat wave. And what's truly fascinating and deeply unsettling, is that we are no longer just looking at higher numbers on a thermometer.
We're looking at something much bigger.
Right. We are watching massive, complex ecosystems and even atmospheric circulation patterns cross thresholds that they may never actually return from.
So to get into this, we've got two incredible sources on the table for you today for this deep dive. And these completely dismantled everything I thought I knew about summer weather.
They really challenge the conventional wisdom.
First, we have a startling on-the-ground dispatch from the journal Nature. It meticulously analyzes the record-smashing 2026 European heat waves. And second, we're pairing that with a truly groundbreaking study out of the journal Science Advances.
Which is just a brilliant piece of research.
It really is. That second paper maps out, in terrifying granular detail, exactly how heat waves have evolved to weaponize wildfires across the western United States.
It's an incredibly revealing combination of data, because when you synthesize these two pieces of research, a very clear, very sobering narrative emerges. We have irrevocably moved past the era where a heat wave was just a fleeting anomaly.
Right. The analogy that hit me like a ton of bricks as I was pouring through these pages is that a modern heat wave isn't just someone sneaking up and turning the thermostat in your house up a few degrees.
No, it's much more aggressive than that.
It's like someone preheating your oven to 500 degrees, leaving the oven door wide open, walking away, and just waiting to see what in your kitchen catches fire first. It's an active preconditioner for disaster.
That's a visceral way to frame it, but based on the physics we're going to discuss, it's highly accurate. So today, we want to peel back the layers of this phenomenon. How has the atmosphere physically changed to allow this?
And how do different places react to it?
Exactly. How do entirely different landscapes, from the concrete streets of London to the dense pine forests of Oregon, respond to this invisible engine? And, what does this mean for the physical reality of the world you're living in?
So let's not talk about hypothetical climate models for the year 2100. Let's talk about right now. Let's look at the visceral, real-time crisis that you've probably seen dominating the headlines. Let's look in Europe.
The Nature piece we have here was published in late June of 2026.
Right smack in the middle of it.
Yes, published right in the middle of what the authors describe as the second unprecedented heat wave to hit the European continent just that year.
Which is crazy to think about.
The sheer scale of the anomaly they are documenting here is difficult to overstate. We are talking about major urban centers pushed to their absolute breaking points. For instance, London approached 40 degrees Celsius.
Oh, wow.
For those of you listening in the U.S., that is about 104 degrees Fahrenheit in London.
Which, if you've ever been to London, is a city famously aggressively not built for that kind of thermal load.
Hmm.
I mean, they don't have widespread residential air conditioning like you'd find in Texas or Florida.
Their infrastructure just traps it all.
Right, the heavy brick buildings, the deep unventilated underground tube stations, it's all historically designed to trap and retain heat to get them through damp, freezing winters. It's not designed to shed heat.
And the nature dispatch is very blunt about the human toll this takes. It's immediate, and it is tragic. Down in France, a town called Pissos recorded its hottest day in recorded history, 44.3 degrees Celsius.
That's pushing 112 degrees Fahrenheit.
And the human cost is explicitly quantified in the source material. At least 54 people dead during this specific window, and the dispatch notes the heartbreaking reality of those deaths.
It's just awful to read.
It is. People dying either directly from physiological heat stress or drowning in rivers and waterways while desperately throwing themselves into the water just to cool off.
It paints this incredibly grim picture of an entire continent under siege by its own sky. But here is where the data completely shattered my expectations. The Nature article highlights an exhaustive study conducted by the World Weather Attribution Group.
Ah, yes, the WWA.
Now, if you aren't familiar, this is an international coalition of top-tier climate scientists who specialize in rapidly analyzing extreme weather events to figure out what drove them. And they didn't just look at London or Paris. They cast a massive net.
They analyzed hard meteorological data from 854 different cities across Europe.
Which is a phenomenally large, robust data set.
To put that in perspective, those 854 cities are home to roughly 30% of the entire European population. This isn't a localized hotspot. This is a continental sample size.
And the findings are just staggering.
Yeah.
Out of those 854 cities, nearly half of them, almost 50%, have either already broken their all-time heat stress records in this single month or are mathematically predicted to do so by the time the month ends.
It's everywhere.
If you look at places like the Czech Republic, Lithuania, Luxembourg, every single city they examined in those nations saw unprecedented, record-shattering highs. Every single one.
When you look at an entire continent simultaneously breaking historical boundaries, it speaks to a systemic shift in the physical rules of the environment. Eric Fisher, a climate scientist at ETH Zurich, is quoted extensively in the Nature piece.
I love his quote in this.
He offers a fantastic visualization to help us comprehend just how thoroughly these records are being demolished.
I absolutely loved his framing here because it gets at the absurdity of the math. He points out that in the normal world, say in sports, breaking a world record is a game of microscopic margins.
You shave 1/100th of a second off a sprint.
Exactly. You jump a centimeter higher. But Fisher looks at the climate data in Europe, and he says it's like watching an Olympic high jumper who is completely pumped full of steroids, walking up to the bar and breaking the world record not by a centimeter, but by half a meter.
It's the statistical equivalent of the athlete leaping over the bar and just continuing to float upward into the sky. It simply shouldn't be physically possible under the old rules of the system.
The historical baseline is essentially irrelevant now.
As Fisher bluntly states in the article, what used to be rare has become a regular event.
Okay, so we have this high jumper on steroids, completely rewriting the record books across an entire continent. The obvious question, the thing I immediately wanted to know, is why?
The mechanics of it.
Yeah, what is the actual mechanical cause of this specific monstrous heat wave? Is the sun just hitting Europe harder?
Not exactly. The Nature piece breaks this down into a few distinct interacting mechanisms. First, on a macroatmospheric level, you have these massive, large-scale air circulation patterns.
Okay.
Laura Wahlberg from the Max Planck Institute explains that you can visualize these patterns as planetary conveyor belts. And right now, these conveyor belts are dragging immense, stifling heat from the equator all the way up toward the normally frigid North Pole.
And Europe just happens to be geographically standing directly in the middle of that conveyor belt.
Precisely. They are catching the brunt of that equatorial transit, but there is a critical secondary mechanism at play here, acting like a roadblock.
A roadblock.
Yeah. Stefan Rahmstorf, a researcher at Potsdam University, points to anomalous dips in sea surface temperatures in the North Atlantic Ocean. When the North Atlantic gets unusually cool patches, it disrupts the flow of the atmosphere above it.
So it blocks the air.
It essentially creates a massive invisible wall that traps all that hot air blowing up from North Africa and the Sahara Desert and parks it directly above the European continent.
So if I'm picturing this, you have the equator actively pumping heat northward. And at the exact same time, you have the ocean building a wall that traps Saharan desert heat in place.
It's literally a meteorological pressure cooker.
But the Nature Dispatch doesn't just blame a couple of weird air currents. They make it abundantly clear that the background state, the actual physical stage this weather is playing out on, has fundamentally changed.
They cite the European State of the Climate Report, which reveals a truly jarring statistic. Europe is currently the fastest warming continent on the planet.
That detail stopped me in my tracks. Faster than anywhere else. Faster than the equator.
With the singular exception of the Arctic. The Arctic is warming at a rate of 0.75 degrees Celsius per decade. But Europe is warming at 0.56 degrees Celsius per decade.
Wait, 0.56? So that's...
A trend that has been holding steady since the mid-90s. That is double the global average pace.
Yeah. Double the global average. So Europe is literally living on a different warming trajectory than the rest of the world. And the Nature piece points out that this extreme background warming creates a brutal, self-reinforcing cycle with the ground itself.
The soil bakes dry.
Right. The high temperatures bake the soil dry. And when the soil is dry, it loses its ability to utilize evaporative cooling. The ground literally loses its ability to sweat.
Yes, the sensible heat flux takes over, meaning the sun's energy goes entirely into heating the air rather than evaporating moisture.
Oh.
But this brings us to perhaps the most fascinating, complex, and frankly tragic paradox outlined in the Nature Dispatch.
I know exactly what you're referring to, and this is the part that totally avoided my understanding of how the climate works.
It's wild, isn't it?
Because if you're listening to this and trying to logic it out, you might be thinking what I was thinking. Okay, if the continent is getting hotter and the soil's drying out, there must be more evaporation happening overall, right?
That makes intuitive sense.
Right, and if there's more water vapor evaporating into the sky, wouldn't that create more cloud cover? And shouldn't those clouds act like a giant natural atmospheric sunshade, blocking the sun and cooling the continent back down?
It is a completely logical, intuitive leap. It's exactly how you'd expect a self-regulating planetary system to operate. But Claire Barnes, an extreme weather researcher at Imperial College London, points to data showing the exact opposite. Cloud cover over Europe has actually significantly declined.
And the reason why the clouds have disappeared is just, it's a gut punch. It's the paradox of clean air.
Exactly. We have to go back to the 1980s. During that era, Europe suffered from horrific smog, particulate pollution, and acid rain, largely driven by sulfur dioxide emissions from coal plants and heavy industry.
It was really bad back then.
In response, governments implemented incredibly strict, highly successful air quality laws. From a pure public health perspective, this was a massive victory. It slashed asthma rates, it cleared the blackened skies, it stopped the acid rain.
But there was a catch.
In doing so, it vastly reduced the amount of aerosol pollution, these tiny microscopic particles floating in the atmosphere.
And this is where we have to do a quick dive into the physics of how a cloud is actually born. Because, as the Nature article explains, water vapor up in the sky doesn't just spontaneously turn into a fluffy white cloud all on its own.
No, it needs a catalyst.
It needs something to cling to. And those microscopic particles of aerosol pollution, they were acting as the scaffolding.
In meteorology, we call them cloud condensation nuclei. Water molecules need a physical surface to condense onto to form a droplet. Dust, sea salt, and yes, sulfate aerosols from pollution provide that surface.
So by cleaning up the air,
By scrubbing the sulfur out of the smokestacks to save human lungs, Europe accidentally removed the microscopic scaffolding that the atmosphere was using to build its sunshade.
cleaner air literally equals fewer clouds.
And fewer clouds mean more of the sun's raw, unfiltered, intense solar radiation is hitting that already proud, unsweating European soil.
It's just an agonizing trade-off. I
Right.
mean, we fix the smog, we save millions from respiratory disease, but in the process, we accidentally clear the skies for the high jumper on steroids to absolutely bake the continent.
It really underscores this terrifying reality that every single element of the climate system is deeply, intricately tethered together.
You pull one thread to fix an isolated problem, and the entire tapestry warps in ways you never saw coming.
Which naturally leads to an intense debate within the scientific community right now, one that the Nature article captures beautifully. The core question is this: has Europe's climate fundamentally, abruptly snapped into a completely new, permanent state?
Right, there's a real debate about the timeline and the shape of this warming. You have Zeke Hausfather, a climate scientist from Berkeley Earth, who was quoted saying that when you look at the data from 1980 onwards, there's this enormous, unmistakable spike in global temperatures centered on Europe.
He calls it glaringly obvious.
Yeah, glaringly obvious. He essentially points to the 80s as a distinct, violent transition point where the old European climate of cool, pleasant, breezy summers effectively died, and this new, brutal climate of extreme heat took its place. A step change.
But on the other side of the debate, the article features Helga Sissling, a climate physicist, who pushes back against the idea of a sudden, stepwise shift. He looks at the same data and argues that we aren't seeing a sudden jump into a new climate regime, but rather a continuous, relentless, compounding warming trend.
So it's more gradual, in his view.
Right. It didn't just snap. It's just getting progressively warmer, day by day, year by year, with no plateau in sight.
And then just to complicate things further, you have Sigaline Berteau from the UK's Met Office throwing another variable into the mix. She suggests that while greenhouse gases are obviously the main driver, there might still be a chance that some of this extreme weather is being exacerbated by natural variations in the Earth's climate cycles.
Which offers a tiny bit of hope.
Meaning, yeah, there is a glimmer of hope that the extreme spikes in warming might slightly slow down at some point if those natural multi-decade ocean cycles shift back to a cooler phase.
Though it's crucial to note how the article frames her point. She emphasizes that regardless of natural variations, Europe will continue to warm as long as global greenhouse gas emissions continue. The baseline is permanently moving up.
The natural variations are just riding on top of a rising elevator.
Exactly. And we are seeing the practical, terrifying effects of that rising elevator in the changing seasonality of these heat waves.
Yes, Eric Fisher points this out. And it feels like something out of a sci-fi novel where the calendar is melting. He notes that these heat waves aren't just getting hotter, they're expanding their territory.
They're starting earlier in the spring and lasting longer into the autumn.
He says the conditions we used to have in August are moving into July and June, and even May in some cases. Summer is literally stretching out, devouring the cooler months.
And researchers are linking this expanding summer and the increasing frequency of these heat patterns directly back to the poles, specifically the shrinking sea ice in the Arctic and the rapid melting of snow cover across Eurasia.
How does that connect to Europe, though?
Well, they argued that the massive, unprecedented loss of millions of square miles of reflective ice and snow is fundamentally altering the temperature gradients of the planet, which in turn disrupts the very air circulation patterns, the conveyor belts above Europe that we talked about earlier.
So the loss of ice in the Arctic is warping the jet stream, which traps the Saharan heat over cities in France and Germany, which are already running hotter because their air is cleaner and their soil has lost the ability to sweat.
It is a masterpiece of disastrous synergy.
Disastrous synergy is exactly the phrase for it, and it provides us with the perfect conceptual bridge to our second source. Because if you want to understand what happens when that exact kind of disastrous synergy moves out of a concrete urban center and collides with a wild combustible landscape, we need to cross the Atlantic.
You read my mind. Let's bring in the Science Advances study focusing on the Western United States. Because in the Nature Dispatch on Europe, the heat wave is primarily framed as a direct, immediate crisis of human health people struggling to physically survive the sheer thermal load of 40-degree temperatures.
But in the American West, this second study reveals how the heat wave acts as a catalyst for a secondary, incredibly destructive physical force.
We are talking about the weaponization of wildfires. What the researchers in this Science Advances paper have done is deliver a masterclass in quantifying exactly how heat waves have evolved from being mere background weather into the active, primary enablers of the modern megafire.
I want to dig straight into the numbers they pulled, because they are nothing short of jaw-dropping.
They really are.
The researchers compiled an immense data set spanning from 2001 to 2024 across the entire Western U.S. They isolated what they call the warm season, running from May through October, and they found that a staggering 42% of all the flood area in the Western U.S. during those months occurred either during a heat wave or within the 5 days immediately following one.
That 42% figure is the anchor of their entire thesis. And to truly grasp why that percentage is so alarming, you have to look at the timing, the temporal distribution.
Because it's not like heat waves happen every day.
Exactly. Heat wave periods, even when you generously include those 5 post-heat wave hangover days, only make up about 12 to 15% of the total days in the warm season, depending on the specific ecoregion you look at.
Right. I was trying to visualize this math for myself, because the disproportionate impact is so massive. Imagine you throw a month-long party at your house. You have dozens of guests coming and going, but there is one specific guest who only shows up for 15% of the party.
Okay, I like this.
Yet somehow, in that tiny fraction of time, That one guest manages to drink 42% of the punch, smash half the furniture, and literally burn down your living room. That guest is punching so far above their weight class, it defies logic.
It's a perfect analogy. That one guest is dictating the entire outcome of the event in a fraction of the time. And what's worse, the study proves that this guest is showing up more frequently, staying longer, and getting significantly more destructive.
Getting worse every year.
Since 2001, the sheer number of heat wave days increased by 91% in forest ecoregions and 76% in non-forest ecoregions. The heat wave season itself, the window between the first heat wave of the year and the last, expanded by 3 to 5 full weeks across the West.
So just like we saw in Europe, the American summer is expanding, stretching its boundaries. But what is this expanding summer actually doing to the physical forests? The study states that over this roughly 2-decade period, total forest burned area across the West increased by roughly 2.5-fold.
Yes. And here's the critical, undeniable linkage the researchers uncovered. Of that massive 2.5-fold increase in total burned forest, 64% of that increase coincides directly with heat waves.
Wow.
If you look specifically at forest burned area during heat wave periods, it has exploded by a factor of 5 since 2001.
Wait, let me make sure I'm wrapping my head around these numbers because
Yep.
they are dense. You're saying total forest fires went up 2.5 times overall, but the fires that are specifically tethered to heat waves went up 5 times?
Correct. The proportion of the total destruction that we can explicitly blame on heat waves is growing at a terrifying rate. In 2001, heat waves accounted for about 27% of all forest burned area. By the end of the study period, they accounted for 44%.
Heat waves are steadily monopolizing the fire season.
And to prove this wasn't just a coincidence, the researchers ran some incredibly sophisticated linear regression models.
Oh, the variance data. This part of the methodology was brilliant.
Yeah.
Walk us through how they actually modeled this without getting too bogged down in the math.
Simply put, they wanted to know how much of the year-to-year variation in forest fires could be explained by one single variable, the number of heat wave days. Think about how many incredibly complex, chaotic factors go into a wildfire season.
Right, you got everything from the shape of the land to a tossed cigarette.
Exactly. You have mountainous topography, shifting wind patterns, lightning strikes, human ignition sources like power lines or campfires, decades of forest mismanagement, long-term multi-year droughts. Yet, despite all that noise, they found that just counting the number of heat wave days alone can mathematically explain 49% of the interannual variance in forest burned area.
Half. I mean, they stripped away the wind, the topography, the campers with matches, and found that half of the reason one fire year is a catastrophe and another year is mild can be chalked up to just how many days the heat wave guest decided to stay at the party.
It isolates the heat wave as the dominant driver. And they took it one step further with what statisticians call counterfactual regression models. Essentially, they asked the math to build an alternate reality. They asked, what if heat waves hadn't increased over the last 2 decades? What if they had just remained flat at historical averages?
And what did that alternate reality look like?
It looked drastically different. The math showed that absent the escalating increase in heat wave days, the cumulative forest burned area in the Western U.S. would have been approximately 37% lower between 2001 and 2024.
37%. You're talking about thousands upon thousands of square miles of old-growth forest, millions of trees, countless wildlife habitats, and entire human communities that would theoretically still be standing today, untouched, if not for the escalating frequency of these heat extremes.
Exactly. So the macro-level correlation is undeniable. The math is robust. But what elevates the Science Advances study from just a statistical report to a true physical autopsy of a fire season is what they do next.
Getting into the nitty-gritty.
Right. They zoom in all the way to the microscopic and atmospheric level. They wanted to dissect the anatomy of a fire-breathing heat wave. If we know the heat wave causes the fire, we need to know how. How does a string of hot, sunny days physically transform a living green forest into a literal powder keg?
Right. And to explain the mechanics of this, the researchers tracked 2 highly specific, crucial fire metrics that spike dangerously during these heat events. The first is vapor pressure deficit, or VPD, and the second is the energy release component, or ERC.
These terms can sound a bit academic, but they are actually incredibly intuitive once you grasp the underlying physics. Let's start with vapor pressure deficit, the VPD.
I love the shorthand for this. I always think of VPD simply as atmospheric thirst.
Atmospheric thirst is probably the most perfect visualization you could use. Technically speaking, VPD measures the gap between the amount of moisture currently floating in the air and the total amount of moisture that air could theoretically hold if it were 100% saturated at that specific temperature.
And the key here is that warm air behaves differently than cold air, right? As the temperature goes up, the air physically expands. And as it expands, its capacity to hold water molecules expands exponentially. It becomes like a giant, dry, fluffy sponge.
Exactly. So during a heat wave, when the temperature absolutely spikes, the atmosphere's capacity to hold water skyrockets. The sponge gets massive. And if there isn't any ambient humidity or rain to fill that expanding sponge, it gets violently thirsty, and it demands water. Where does it get it?
It steals it. It literally sucks the moisture right out of the physical landscape. It pulls the water out of the leaves on the trees through their stomata. It sucks the dew off the grass. It evaporates the water from the topsoil. The higher the VPD, the more aggressively, almost violently, the atmosphere is robbing the ground of its moisture.
And the study shows that VPD is significantly universally elevated during heat waves across the entire Western U.S. domain.
Which perfectly sets the stage for the second crucial metric, the energy release component, the ERC. If VPD is the invisible thief stealing the water, ERC is the measurement of the highly explosive bomb that the thief leaves behind.
That's exactly it. How does the National Fire Danger Rating System define ERC?
Formally, ERC relates to the available energy per unit area within the flaming front at the head of a wildfire. It measures how hot and how fast the fire will burn.
But functionally, in the field, it is a composite metric that is heavily, almost entirely weighted toward the moisture content of dead, fallen wood. Specifically, what wildland firefighters call 100-hour and 1,000-hour dead fuels.
Okay, stop there. Break those terms down for us. What is a 100-hour fuel versus a 1,000-hour fuel?
These are classifications based on how long it takes a piece of dead organic matter to react to changes in the environment. A 1-hour fuel is something tiny and fragile. Think of a single blade of dry grass or a fallen pine needle. If the sun comes out, that pine needle will be bone dry and ready to ignite in about an hour. It reacts instantly.
Makes sense.
But a 1,000-hour fuel is completely different. Picture a massive, heavy, dead oak or pine log lying on the forest floor, maybe 3 feet in diameter. It has thick bark, dense core rings. It's partially buried in the dirt. It takes a long, incredibly sustained period of intense drying, hundreds of hours, essentially a multi-day heat wave, for that atmospheric thirst, the VPD, to slowly pull the moisture all the way out of the deep, dense core of that massive log.
So when the researchers see the ERC metric spiking during a heat wave, it's an alarm bell. It means the heat has been so intense and so sustained that those big, heavy 1,000-hour logs, the massive timbers that normally retain moisture and actually resist burning, have been baked entirely dry.
The total volume of wood available to combust hasn't just gone up a little, it has skyrocketed.
And that profound drying process leads directly to one of the most critical, dangerous mechanisms the researchers highlight in the study, the catastrophic loss of the nighttime thermal barrier.
This part of the study is genuinely terrifying, especially if you know anyone who works in wildland firefighting. Because traditionally, historically, nighttime is the reset button. It's the relief period. The sun goes down, the temperature drops, the relative humidity naturally rises, and the fire physically calms down.
Firefighters call it laying down.
The flames drop, the spread slows, and it gives the crews a tactical window to build containment lines and get ahead of the beast.
That was the old paradigm of fire behavior. But these modern heat waves fundamentally alter the diurnal cycle, the natural daily rhythm of the Earth's weather. During a severe heat wave, you essentially have a massive, stagnant dome of high-pressure warm air sitting over the entire region like a lid.
What happens under that lid is that the normal winds often completely calm down, and that stagnation promotes the formation of what meteorologists call nighttime thermal belts.
Okay, let's translate that. What does a thermal belt mean for the firefighters actually standing on the ground?
It means the relief never comes. The warm air gets trapped along the lower and mid-elevation slopes of the mountains, which is exactly where the dense forests are. Those zones simply do not cool down when the sun sets.
It just stays hot.
And because the temperature stays artificially high all night, the vapor pressure deficit, that relentless atmospheric thirst, never recovers. The invisible sponge never shrinks. The atmosphere continues sucking moisture out of the pine needles and the 1,000-hour logs at 2 a.m., just like it was doing at 2 p.m.
So the fire doesn't lay down. It just keeps ripping through the timber in the pitch black. The firefighters completely lose their tactical advantage. The study explicitly states that this loss of nighttime recovery enables massive, sustained, overnight burning periods, which directly translates to exponential, uncontrollable fire growth.
It's a nightmare scenario.
But wait, I want to push back on this premise just a little bit. Because if you've lived anywhere with hot summers, you know that heat waves don't usually just fade away quietly into a sunny, mild Tuesday. They build and build until the pressure is unbearable, and then they usually break with a massive, violent thunderstorm.
True.
The sky turns black, the wind whips up, the thunder cracks, and the rain comes down in absolute buckets. Shouldn't that massive downpour just put the fire out, or at least soak the 100-hour fuels enough to stop the spread?
In a normal, temperate weather pattern, a thunderstorm is exactly what you'd want. But these heat waves create a highly specific, uniquely dangerous atmospheric profile. The researchers dive into the meteorology here.
And what do they find?
They point out that the massive high-pressure ridges that cause the heat waves in the first place also induce severe instability in the lower and mid-troposphere. This instability forces the air upward, often over mountain ranges, in a process known as orographic lifting.
Wait, orographic lifting, that's just a technical way of saying the wind hits the side of a mountain, has nowhere to go but up, and as it gets pushed up into the colder atmosphere, it condenses into a storm cloud, right?
That is exactly it. So these heat waves are actively generating thunderstorms high above the peaks.
Okay, so the storm is there, the clouds are there. Where's the rain?
This is where we encounter one of the most frightening phenomena in nature: dry lightning. The thunderstorm is raging high up in the atmosphere. It is actively generating heavy rain. But remember the vapor pressure deficit. The air sitting right above the ground is so fiercely hot and so violently thirsty that as the raindrops fall from the cloud, they literally evaporate in midair before they ever touch the earth.
It's called virga, isn't it? You can sometimes actually see it. These dark, beautiful curtains of rain falling from the bottom of the cloud, but they just sort of ghost out and vanish halfway down the sky.
Yes, Berger. The water completely evaporates, but the lightning does not. The lightning bolts make it all the way to the ground. And what exactly are they striking? They were striking a landscape where the 1-hour grass, the 100-hour branches, and the massive 1,000-hour logs have just been pre-baked in an oven for 5 straight days.
The researchers actually quantified this phenomenon, which is incredible. They pulled millions of data points from the National Lightning Detection Network and cross-referenced them with incredibly precise precipitation grids.
They define a dry lightning strike as any cloud-to-ground hit that occurred with less than 2.5 millimeters of accumulated rainfall that day.
And they found that these dry lightning strikes increase exponentially relative to normal conditions across the vast majority of the Western U.S. during and immediately after heat waves.
The ratios they uncovered are staggering. If you look at the dense forest ecoregions of Western Oregon, Washington, and Northern California, the counts of wildfires directly caused by lightning increased by more than 5-fold during heat waves compared to baseline conditions.
It is the ultimate catastrophic, disastrous synergy. Think about the sequence of events here. The heat wave rolls in, it spikes the atmospheric thirst, it pre-bakes the landscape, it dries out the giant logs that normally wouldn't burn, it erases the nighttime cooling barrier.
And then, as its grand finale,
It violently pushes the air up the mountains to literally summon the dry lightning storms that act as the ignition source. It is the architect, the builder, and the arsonist of its own destruction.
it is a perfectly engineered mechanism for mega fires. And yet, the researchers discovered something even more insidious about this entire sequence, a concept they term moisture memory.
Right, because earlier when we were talking about the timeline of the data, we established that the researchers didn't just look at the days the heat wave was active. They looked at the heat wave period, plus the 5 days immediately after it officially ended.
And my first thought was, why look at the 5 days after?
If the heat wave is broken, if the cold front has moved in, isn't the danger over?
You would assume so, especially if you step outside and the temperature feels suddenly normal and pleasant. But we have to go back to the ERC, the energy release component, that tracks those massive 1,000-hour logs. The study definitively shows that in regions like the Pacific Northwest and California, the ERC remains critically significantly elevated for many days following the conclusion of the heat wave.
Even after the temperature has plummeted.
Even after the temperature drops and the relative humidity goes back up to normal levels. Because you have to think about the physical reality of a giant 3-foot-thick tree trunk. It takes hundreds of hours of intense heat to pull the moisture out of the deep core of that wood. Consequently, it takes an equally long time for ambient moisture in the air to slowly seep back into the core.
That makes total sense.
Those heavy fuels have moisture memory. They physically remember the trauma of the heat wave for days after the meteorological event is technically over.
So, picture this scenario. A dry lightning strike hits a remote ridge in Oregon 2 days after the heat wave breaks. To a hiker walking by, the weather feels totally fine. It's 75 degrees and breezy. But when that lightning hits the forest floor, the woods are still primed to explode because internally the logs are still bone dry.
Exactly. And this moisture memory explains a fascinating, terrifying quirk in the data. In forest ecoregions, the aggregated burned area doesn't peak on the hottest day of the heat wave. It actually peaks 7 days after the onset of the heat wave.
7 days later.
The fires that ignite during the peak heat don't just burn and die out. They continue to spread with sustained, nonlinear, explosive growth in the days following, entirely because those heavy fuels are still actively sustaining the combustion.
It is a relentless, unforgiving mechanism. But this brings us to an incredibly interesting divergence in the data, a nuance that the Science Advances study explores beautifully as they dig deeper. Because if extreme dry conditions are the primary culprit for this destruction, we have to ask a logical question.
Are all heat waves created equal?
And furthermore, do all natural landscapes react to heat waves in the exact same way?
The short answer to both of those questions is no. And the researchers did something brilliant with their methodology here to prove it. They took their massive database of heat waves and they rigidly separated them into two distinct categories: dry heat waves and moist heat waves.
I have to admit, until I read this paper, I didn't even know a moist heat wave was a phenomenon in the Western U.S. It sounds like something you'd experience in a swamp in Florida, not in Idaho. It sounds miserable.
From a human comfort perspective, it is. They define a dry heat wave as an event where the daily average minimum relative humidity ranks in the bottom 25th percentile for the warm season. Extremely dry air.
Right.
A moist heat wave, conversely, is when the humidity sits in the top 75th percentile. The air is hot, but it's loaded with water vapor. And the difference in how these two types of heat waves impact the physical landscape is profound.
The data is stark. During dry heat waves, the total burned area is astronomically higher than baseline conditions across almost every single ecoregion they studied. But during moist heat waves, the dense forest ecoregions actually experience a reduction in burned area compared to baseline.
The heavy moisture in the air actually acts as a dampener on the fire weather. The 1,000-hour fuels don't dry out.
However, there is one incredibly important, counterintuitive exception to this rule, and it perfectly illustrates how different ecosystems function.
Yes, the Great Basin.
While those moist heat waves reduce fire risk in the deep forests of the Cascades, they actively promote massive increases in burned area in the non-forest ecoregions, specifically places like the Great Basin. In fact, moist heat waves increase fire size there by up to 4-fold.
Wait. Pause. How is a moist heat wave sparking massive, uncontrolled fires in the sagebrush of the Great Basin, but simultaneously suppressing fires in the dense pine forests of Washington? That feels like a contradiction.
It sounds like one until you look at the absolute baseline dryness of the environment itself. The Great Basin is inherently an arid, desert-like ecosystem. So even a quote-unquote moist heat wave there, meaning the 75th percentile of humidity for that specific dry region, is still objectively very dry air when compared to a coastal forest.
It simply isn't wet enough to stop fine 1-hour fuels like invasive grasses and dry shrubs from being highly flammable.
Ah, I see. And because it is still fundamentally a heat wave, the high-pressure ridge is still there, which means it is still forcing orographic lifting, which means it is still summoning the dry lightning.
So you have massive thunderstorms rolling over the Great Basin, hurling lightning bolts down into the dry sagebrush, and the moist air isn't remotely moist enough to stop the grass from catching fire.
Precisely. Which brings us to the core fundamental difference between how these two types of landscapes operate. The researchers outline this beautifully. The Great Basin, the shrubby, grassy, non-forest ecosystem, operates as what we call a fuel-limited system.
Let me try to build an analogy here to make sure I fully grasp the mechanics of this. A fuel-limited ecosystem is essentially like a brick fireplace that has no wood in it.
I love this analogy.
It doesn't matter how hot your match is or how many matches you strike and throw into the grate. If there is no wood in the fireplace, you aren't going to get a fire.
That is a perfect translation of the ecology. In these non-forest, fuel-limited ecosystems, the occurrence of massive burned areas isn't actually dependent on how hot the summer is. It's mostly dependent on what happened the previous winter.
Oh, because of the rain.
If the region experiences a really wet, rainy winter and spring, it triggers a massive, explosive growing season. A huge crop of fine grasses blankets the desert floor. Then summer inevitably arrives, all those grasses die and turn bone dry, and now you suddenly have a fireplace completely stuffed with kindling.
So for the Great Basin, a heat wave with dry lightning will absolutely spark a fire. But the total size of that fire from year to year isn't really driven by the temperature of the heat wave. It's driven by how much grass grew 6 months ago.
Which perfectly explains why, in the study's historical data, non-forest burned area hasn't actually increased all that much over the last 2 decades, even though heat waves have become far more frequent.
The matches are being thrown more often, the fireplace is hotter, but the total amount of wood available to burn hasn't fundamentally changed.
Exactly. But now, contrast that dynamic with the dense timberlands. The researchers classify forest ecosystems not as fuel limited, but as flammability limited.
So, to follow the analogy, a flammability-limited forest isn't an empty fireplace. It's a giant, dense, multi-story log cabin. The fuel is always there. It's ubiquitous.
There are millions of mature trees, decades of accumulated pine needles on the forest floor, millions of fallen branches. The wood is eternally sitting in the fireplace.
The only reason the entire forest isn't burning to the ground every single day is because the wood is naturally too wet to catch fire. The moisture is the only defense.
That's it. The forest requires an extreme event, the heat wave, to strip the protective moisture out of the cabin walls so they can finally ignite. And because the sheer volume of fuel in a forest is essentially limitless, every single time you add another day to a heat wave, you unlock thousands of tons of new fuel for combustion.
You dry out a deeper layer of the soil, you dry out a thicker log.
Which brings us full circle and entirely explains that terrifying mathematical variance we talked about earlier, the fact that 49% of the variation in forest fire size is tied directly and exclusively to the number of heat wave days. The heat is acting as the lockpick.
It is picking the lock on the forest's natural ancient defense mechanism.
And here is where we arrive at what I consider the most alarming existential trend line in the entire Science Advances paper. The atmosphere itself is actively evolving to become much, much better at picking that lock.
You're talking about the trend lines when they mapped out the dry versus moist heat waves over the 24-year study period.
Yes. The researchers found that the frequency of moist heat waves, the ones that tend to dampen fire risk in the forests, do not exhibit any significant upward trend over the study period. Their frequency is essentially flat.
But the dry heat wave.
The dry heat waves, the specific meteorological events engineered to extract maximum moisture and cause massive destruction in places like Washington, Oregon, and California, those have increased fivefold in forest ecoregions since 2001.
A five-fold increase in the exact specific type of weather event mathematically proven to burn down a forest. And the paper makes a point to note that the daily minimum relative humidity during these heat waves is steadily, significantly dropping year after year.
Right. It declined by 0.08% per year, every year, in forest ecoregions. And crucially, those declines in humidity were most pronounced in the exact geographic locations where the burned area increases were the highest.
The researchers state it plainly, without any academic hedging. Progressively drier heat waves have become more effective in amplifying fire risk. The atmosphere is literally, measurably learning how to burn the woods down more efficiently.
It is a phenomenal, rigorous, and frankly horrifying data set. And when you sit with it, it forces you to fundamentally rewrite how you view these everyday weather events.
If we take a step back and synthesize the journey we've been on with both of our sources today for this deep dive, the overarching trajectory of our planet is unmistakable.
It's all connected.
We started by looking at the urban centers of Europe through the Nature Dispatch, where we confronted the startling realization that the continent's climate didn't just get a little warmer, it fundamentally shifted into a new state.
We saw the high jumper on steroids, enabled by the tragic paradox of cleaner aerosol-free air, breaking historical temperature records by unimaginable margins.
We saw an entire continent warming twice as fast as the rest of the globe, trapped beneath stalled weather patterns and blocking ridges that pull Saharan heat into cities entirely unequipped for it.
We felt the sheer, oppressive, physical weight of that 40-degree-Celsius heat pressing down on the brick streets of London.
And then we crossed the Atlantic, moving from the concrete to the timberline with the Science Advances paper, and we discovered that a heat wave is not just a passive, oppressive blanket of weather. In the right landscape, it is the active mechanical architect of the modern megafire.
We met the 15% guest who drinks 42% of the punch. We mapped out the exact, relentless mechanism that spikes the atmospheric thirst, bakes the 1,000-hour heavy fuels, entirely erases the nighttime thermal barrier that firefighters rely on, and then violently pushes the air up the mountains to summon the dry lightning.
All while leaving behind a moisture memory that keeps the landscape primed to explode for days after the thermometer drops back to normal.
When you lay it all out like that, it forces a complete systemic reassessment of how society interacts with and prepares for extreme heat.
Which leaves us with a final, I think, truly paradigm-shifting question for you to mull over the next time you check the summer forecast.
Right now, our operational fire early warning systems, things like the red flag warnings issued by the National Weather Service in the United States, they are built around very specific, immediate thresholds. They trigger the alarm when the wind speed hits a certain knot and the relative humidity drops below a certain percentage on a given afternoon.
But heat waves themselves, the actual prolonged, compounding temperature extremes, are not directly codified into those official fire warnings.
Because those warning systems were historically designed around the immediate tactical minute-by-minute drivers of fire spread, rather than the long-term strategic landscape-level preconditioning of the fuels.
Right. The alarm rings when the fire is already imminent, but based on every single piece of data we've just unpacked, if a heat wave is the ultimate catalyst, if it is the invisible, relentless engine that pre-bakes the landscape, erases the nighttime relief, and actively summons the lightning that starts the fire, do we need to completely, radically rewrite the way we warn the public about the weather?
The data strongly suggests that our current operational systems might be missing the most critical, foundational part of the entire disaster sequence.
Exactly. What if the most dangerous fire alarm isn't the gale force wind howling through the canopy of the trees? What if the most dangerous, urgent alarm is the invisible, silent, compounding preheating of the world all around us?
It brings us right back to that heavy, oppressive feeling we talked about at the very beginning of this deep dive. When you walk outside and the air feels like a physical weight, we simply cannot afford to look at it as just uncomfortable weather anymore.
The oven is preheating. The door has been left wide open.
The only question left is what catches fire next.
Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.